What's up, guys? This is Irene Aldridge, and I'm, of course, a co-author of Big Data Science in Finance book that you can see behind me. It's available on Amazon. But today I want to talk about LASSO. And LASSO stands, it's a very complicated acronym. It actually stands for Least Absolute Shrinkage and Selection Operator. But most importantly, what it helps do, it helps prevent certain overfitting problems. So I'm going to share my screen now with you and show you what I mean. Okay, so here's the screen. So last time we talked about neural networks and how when you train a neural network that we did together on 2 years of data, and then provide any input data, out of sample input data to that model, all you get is one flat line. You get the same result no matter what the input is. So, and this is what's called overfitting, when your network is so tightly fit to the data that cannot think on its own anymore. It doesn't matter what data you feed it, it just produces basically garbage. Okay, and here's a more graphical example of overfitting, where in this case you stitch your mattress and your bed so close that you basically have zero room for movement. Okay, so there are ways to deal with this problem, and one of them is this lasso that's described in chapter 3 in our book. And this is what you see is online on our book website. Our book website is best accessed by typing in bigdatafinancebook.com. Okay, and we have code there for you and everything. So this is for chapter 3. And we're going to use this lasso. So what I want to emphasize in this lasso, so the way lasso is helping, and we're explaining it in detail in the book, of course, in chapter 3, but the way lasso is different and helps actually prevent overfitting is it imposes a penalty. Okay, so here's your traditional linear regression. I'm going to make it slightly bigger so you can see it better. Here's your traditional linear regression, y equals bx plus epsilon, where our objective is to find beta hat, which is the estimate of the coefficients that relate x and y. And we usually find this by optimizing the quadratic loss function. And so these are resulting coefficients. But lasso adds another term to that function, to the loss function that we're going to minimize. And this loss function is lambda, which is some coefficient you select. Most often it's set to 1, sum of the absolute values of all the coefficients. Okay, so what happens here, the bigger are your coefficients, means the more important are your variables, right? The independent variables that you're using in your regression, the more room your loss function is going to have to actually vary the data. And on the other hand, the smaller your beta coefficients, right? Doesn't matter, positive smaller or negative smaller, then the less room, the tighter is going to be your loss. So the less meaningful coefficients are going to get tighter fit, and the more meaningful coefficients are going to get a better fit. All right, so this basically this extra term, that's what gives us extra room for movement in our regression. And then this beta hat is what actually we end up optimizing. So how are we going to run this? Well, it's actually pretty straightforward. So first we're going to install this sklearn, okay? And this stands for scikit-learn. It's an awesome Python library, completely free, and you can do a lot of different modeling with this stuff. So in our code, we're going to import from sklearn linear model, import lasso. We're going to instantiate this model equals lasso. And then we're going to specify the evaluation method. Let me make it a little bit smaller because it doesn't fit on this page. So again, all this code is available on our book website, which is bigdatafinancebook.com. So we have model lasso, and then we're going to specify the evaluation. So here we're using a k-fold valuation. And what this means is we're going to break the data into in this case, we're splitting it into 10 different subsets. And we're going to run our model on that. We're going to use cross-validation score, which we also discuss in the book, but I'm going to talk about another time. Okay. And then we're going to use the window, a rolling window estimator, and use this lasso on the same data that we use for neural networks, which is IBM returns and SPY returns combined. And this is daily data from Yahoo. And we're going to evaluate performance. We're going to create the same strategies we did last time with neural networks. So if the predicted value by this lasso model is greater than 0, we're going to buy that IBM stock, okay, and hold it for 1 day. And if the predicted value is less than 10, then we're going to short sell IBM stock also for 1 day, okay? And this target data, of course, is our actual realized return, and that's how we measure the performance. So this is a gross performance. We're not accounting for transaction costs. Of course, the Yahoo data is also very much been researched over. Yahoo has made daily data publicly available probably close to 2 decades ago. So there've been several generations of finance researchers who've been mining and mining and mining the data. Now we're going to start with the most popular windows. Like if you go to equity research analysis, most equity research loves doing 20-day trading day windows and 50-day trading windows. There are a lot of models like moving average crossovers that are based on 20 and 50 days, etc. So if we do the 20-day realized versus predicted, we don't really, we see basically a big blob. If we do 50-day, we also see a giant blob, and this is the corresponding 20-day cumulative strategy performance. And this is the corresponding 50-day cumulative strategy performance. In both cases, you know, it's nothing to write home about, rather kind of a sad looking thing. All right, so, but what I want to show you is if you actually go out of your regular comfort zone, 20 and 50 days, and you actually start doing 10-day rolling window, there's still significant performance, right? So it's worth experimenting with different window resolutions to see what kind of results you get. So this is IBM performance with Lasso, okay? And this is from 93 to 2020. And this is looking a lot better. Now, this, interestingly enough, is a 5-day rolling window. So we're getting a reversal. If in a 10-day window is showing us a strong momentum in IBM using Lasso, in 5-day window, it's actually showing us a strong reversal. This is a 150-day, which is basically 1 year. Okay, it's kind of could be better. But this is a 500 trading days, which is 2 years. Okay, so it wasn't so sharp until 2009, but it's been a pretty nice looking since. Of course, if we train our strategy on 5 years of trading days, then it actually looks even better, right? So bottom line is it's worth to evaluate these models with different window resolutions. And today we learned how one of the ways to mitigate the overfitting problem in the basic case of linear regression using this lasso technique. This technique is very popular in data science. And it occurs in different applications, not just financial, but you can use it next time instead of using linear regression, and it will give you better results with greater confidence. Okay, thanks so much. It's great to see you all, and I hope to see you again. And please subscribe to my channel and check out the book and check out the website. Okay, thank you, and always a pleasure. Take care.